So let's say that I have two dice, and I roll the two dice, and I ask the following question. So I want to find out the probability of getting at least 1 6 when I roll the two fair die. So how can I approach this problem, right? Well, how can I get at least 1 6? Well, there's basically two possibilities. Either I could roll a 6 with the first die, or I could roll a 6 with the second die. So really this is the same as the probability that the first die is 6, or the second die is 6. Okay, so that's another way to rephrase this question. So now it's tempting, if you are not careful about your probability calculations, to say, right, I know that the probability that the first die is 6 is 1 6th, and I know that the probability that the second die shows a 6 is 1 6th. So I want either one of these things to happen, so really I just should add up the probabilities, right? I'm just looking at either one of these events happening, and so then I'm guessing that maybe that this is true, right? That the probability that I get at least 1 6 is 1 over 6 plus 1 over 6, which is 1 over 3. But this is wrong. Okay, so where did I make the mistake here? Well, I made the mistake at this point, right? I can't just say that the probability of the first die being a 6 or the second die being a 6 is the sum of the individual probabilities, right? So my mistake here is that this is not true in general. The probability of A or B is not the same as the probability of A plus the probability of B in general. Okay, so what we're going to look at in this lesson is, well, what is true for the probability of A or B. Let's look at this example in a little bit more detail and see exactly why this is not true. So let's look at the sample space. So remember, we're rolling two fair die, and the sample space, we can represent it with a two-way table, and I'll sketch that two-way table here. So here's our sample space represented as a two-way table. So each rectangular cell represents an outcome, and the number above the diagonal is the number on the first die, and the number below the diagonal is the number on the second die. So for example, this cell here that I've circled in green represents the outcome. The first die is 2 and the second die is 3. Okay, so why is it that the probability of rolling at least 1 6 is not just twice the probability of rolling a 6? Well, let's look at the successful outcomes. The probability of rolling at least 1 6, well, I'll circle all those outcomes in red, or I'll outline them in red. So we could have all the cells on the bottom row and all the cells on the last column, right? So those are all the cells that have at least 1 6 in them. And if we count them up, you see that there's 11 of those cells. So so this probability up here, actually, this probability, the probability of rolling at least 1 6, you scroll down a little bit there, that's actually equal to 11 over 36, because there's 36 total possible outcomes, and 11 of them are successful. And you see the probability of the first die showing a 6, well, that's all these ones down here, so I'll just fill those in, right? So there's 6 of those, and the probability of the second die showing a 6, well, if we wanted to calculate that on its own, we just have 6 of them here as well, right? And so you see the reason that we don't add up the two probabilities is that if we did that, effectively we'd be double counting this one here, the overlap. Okay, so that's the real reason why this is not true, is that if we were to add up the probabilities, then we're double counting the overlap. We're double counting the A intersection B. Okay, we're counting that twice when we should only be counting it once. So that tells us really what the proper addition rule should be. We don't want to double count the overlap. So if we just add them up, then what we've just observed here is that essentially we're counting this overlap twice, and we only want to count it once. So to compensate for that, we just subtract that probability from the right-hand side here. And that gives us the correct addition rule. So here's the addition rule for probabilities. It says that the probability of A or B, if we have two events A and B, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, so let's use this in an example. So let's say that we draw a card from a standard 52 card deck, and the question is, what's the probability of getting either a spade or a face card? So this is a situation where we could use the addition law if we wanted. You could work this out without the addition law, because you can just list off all the successful outcomes and divide by the total number of outcomes. They're all equally likely. But we're going to do it using the addition law just to show how that works. So we have two things here. We have the probability of getting a spade, and we have the probability of getting a face card. Right? So let's work those out first. So the probability of a spade, well, how many spades are there in a 52 card deck? There are 13. So the probability of getting a spade is 13 over 52. And how many face cards are there? Well, the probability of getting a face card, so how many face cards? Well, each suit has 3 face cards, right? So face cards are Jack, Queen, or King. So we have 3 face cards in each suit, and there are 4 suits, so there are 12 face cards. So the probability of getting a face card is 12 over 52. Now we want to work out the probability of getting a spade or a face card. So the probability of a spade or a face card, right? According to the addition law, it's the probability of a spade plus the probability of a face card, I'll just put face there, minus the probability of both, the probability of face card and a spade. So now we've already worked out 2 of the things on the right hand side here. We have 13 over 52 plus 12 over 52. And what about the probability of a face card and a spade? So again, we just need to work out how many cards are both face cards and spades. So how many spades are face cards? Well, 3 of them. So we get 3, and the total number of outcomes is 52. So 3 over 52 there. And now we just do the arithmetic. We have 12 plus 13 minus 3, so that's 22 over 52. So that's the answer, right? The probability of getting a spade or a face card when you draw a single card from a standard deck is 22 over 52. Now you could do this directly just by counting up the total number of cards that are either spades or face cards, and you'll find that there are exactly 22. So that will agree with this calculation here. But we just wanted to use this as a demonstration of the addition law for probabilities.